3E. 12th already, right?
Yeah.
So, take two of these.
Right on these as I'm giving the lecture.
In. So we're in section 3.4. I want you to think a little bit about coordinate systems. So, I'll take two. So if I say x equals 1, 3, really what we've done is we've given you enough information to draw a picture of x. So if that's 1, so there's the point 1, 3. And then we draw the arrow from the origin to that point. So knowing where this lives is relative to an XY coordinate system. Okay, but nothing says that X and Y have to look like this. Is I could make another XY coordinate system. Let's call this X hat and Y hat. And I could go 1, 2, 3, 4 units this way, 2 units that way, and draw the arrow there. So this graph paper I passed out, and I'm going to grab a copy here. I'm going to put one copy up here so I can keep referring to it. Okay, we've got two different coordinate systems superimposed on each other. So what I want you to see here is we've got the normal XY coordinate system. Let's do this for a bit. So here's regular XY. We also have another coordinate system called x hat, y hat. And then we've got our tick marks. 1, 2, 3, -1, -2, 1, 2, 3, 4, -1, -2. And on this one, we also have our tick marks. There's 1, 2, -1, 2, -2. Okay, so a coordinate system is or two-dimensional coordinate system is an x direction and a y direction. So what direction positive x faces, what direction positive y faces, and a distance to represent one unit along that axis.
This is sort of familiar to me when I use Blender. There's a local.
Yeah, that's exactly what's going on.
Okay, and then there's a global.
Right.
Okay, so this is okay.
It's exactly what it is. So we'll just have different frames of reference when we're describing the same point. Yeah, you're going to get a lot out of this. Take 2. You're going to get a lot out of this class. So you'll be relating it to the Blender work. Okay, so for a coordinate system, we need a direction for the x-axis and what counts as one unit in that direction, a direction for the y-axis, and what counts as one unit in the y direction. And that can be described by vectors. So for this coordinate system, let's go back to so what this means is, so there's the 1, 0 vector. Its direction tells us the direction of positive x. Its length tells us what's one unit in the positive x direction. Actually, I'm going to change this slightly. Let's do this first. So if you give me 2 vectors, I can completely build the coordinate system. So if I'm given these 2, yeah, delete this for now, come back to it. Is there's my x-axis vectors. And I can turn them around. Here's my y-axis vectors. So if I stack these up, that's the x-axis, that's the y-axis, and every one of those vectors gives me a tick mark. And I could do a bit smaller. So I can also build up a coordinate system. So I'll just keep putting these together. Put those together. So there's positive x, 1, 2, 3, 4. And of course, negative x would go this way with a negative 1, negative 2. There's my y-axis, and positive y and negative y go this way. So hopefully you see that a pair of vectors will define a coordinate system. But sometimes you want different scales. So maybe you'll want something like one unit in the x direction is big, one unit in the y direction is small. And to indicate it's a different x and y coordinate system compared to the standard one, we'll use hats. Okay, but remember, we said officially vectors are arrows, but it's going to be much easier to represent them with coordinates. So this x-axis vector makes the standard x-axis is really 1, 0. And this y-axis is really 0, 1. Okay, and if we're here, and I'm going back to that graph paper I gave you, it's 1. So this is the point 2, 1, 1, 2. Yeah. So this vector is 2, 1. Okay, and notice that the x-axis vector and the y-axis vector form a basis for R2. So anything in R2 is a linear combination of these two vectors. So I'll go V for now. So when I'm talking about a coordinate system for a space, it's I can describe that coordinate system by a basis, just a collection of vectors. First vector represents the x-axis, second vector is the y-axis. Okay, so actually, let me go back to this picture. I'm going to pick a point here. Let's do this in brown. Same point over here. And then I want to draw same vector here. Right, so just so we're clear. Let's move these down a little bit. So this is my vector v, and I'm doing a copy here and a copy there. Relative to the standard coordinate system, the endpoint of v is 3, 4. And relative to this new coordinate system, the endpoint of v is 2, 1. Make sure you see this. Is to get to this endpoint, I go 3 in the x, 4 in the y. Or if I'm working in the new coordinate system, to get to this endpoint, it's 2 in the x, 1 in the y. Okay, so we give names to these. So the standard coordinate system, 1, 0, 0, 1. It's called S. For this particular part of the lecture. The new coordinate system called B. So S always stands for the standard coordinate system. And this will stand for different coordinate systems. So in this particular example, B is this one. In a different problem, S will always be this, and the B will change. Okay, so we write this fact. If I want to describe how to get from the origin to the end point of V relative to the standard coordinate system, it's over 3, up 4. 3 in the x, 4 in the y. And if I want to describe how to get to that same vector relative to the new coordinate system, it's over 2, up 1. So I want to emphasize it's the same vector. It's just when we're so the vector is the picture. It's the drawing of the arrow. And we want to describe that arrow with a matrix. And the description is going to depend on what coordinate system we use. Okay, so let's grab a copy of these. Just a tad. Let's see. Trying to find a good one here. Okay, so I've got a description of the V vector relative to S, and I want to get the description of the same vector relative to B. Let me grab these. Okay, so 3, -1 is this in green here. So there's the value. Probably. So I'm not even sure. So I'm going to draw that same vector over here. Yeah, good. Way ahead of me. Okay, so notice this is the same vector. But now it's this point is over 1 and down 2. So the coordinates of V relative to B are 1, -2. The same vector, just the first description is relative to the standard coordinate system, and we want the description relative to the new coordinate system. And let me try to find another one here. Same coordinate systems. Let's grab this right here. Okay, so you know the coordinates of V relative to B are 0, 2. We want to find the coordinates relative to S. Okay, so let's draw the picture. Our V is, we go up here to 0, 2. Our V looks like that. Draw the same V over here. And this point is -2, 4. Okay, so you get the idea. The vector is floating out there as an arrow. if you want to describe the arrow to somebody, you have to do it relative to a coordinate system. And here we're talking about alternative coordinate systems. Question? Uh-huh. On the blue graph? No, I'm talking about, I had to draw it a little bit. I'm talking about this point. No, this point's on the y-axis.
I think this question is about how the axis is scaled. Because if you're going up 2 squares is 1 unit, but if you're going down 2 squares is.
Oh, I see what you're saying. Yeah, thank you. You're right. So yeah, that's just, yeah, good point. Yeah, so that should have been fixed on all of these. Yeah, thanks for noticing that.
Which one would you consider helpful and which one would you consider helpful?
Doesn't matter.
Oh, it doesn't matter.
Yeah, just two different coordinate systems. Yeah, probably this would be global and this would be local.
Okay.
But it really, in some sense, it's just you're working with two different systems. You're comfortable with those. Oh, and then just one more notation. So before we knew anything about more coordinate systems, so we didn't know other coordinate systems existed. We would just write V equals 3, 2. So So these two statements say the same thing. Okay, so we have two general types of problems. So there's some vector that we have in mind. We know the coordinates relative to one coordinate system. I mean, we get the coordinates relative to a different coordinate system. Okay, so let's try this again. Remember that we're given B is 2, 1. Okay. So when we say the coordinates of V relative to B are 0, 2, that means this V vector is 0 along the 2, 1 direction plus 2 along the negative 1, 2 direction. That's essentially what a coordinate system means. So when you have the coordinates, it's how far you stretch the x vector, and then you add to that the y vector stretched by a certain amount. And then we saw we had a nice notation for linear combinations. And then if we work this out, this is negative 2, 4. So remember, 0, 2 is our description here. We take that same point and calculate it relative to the red system. It's the point negative 2, 4. So here's the calculation. And now, if we look at it the right way, we can say this matrix transforms B coordinates to S. And this is going to come up, probably in almost every lecture from now to the end of the semester. I'm going to call this the beta S matrix. And one thing I want you to notice here there's B. And there's the beta S matrix. So now notice how easy it is to go from the basis representing the coordinate system to the matrix that transforms coordinates for you. So what do you think the matrix that transforms S to B is going to be? How do I use the beta S matrix to get the S to B matrix? Very close. Inverse. So just the opposite problem. And then remember, we have the shortcut rule. So the second problem, or the first problem, I guess it would be, so it's this point and that vector. Take it over here. in this new coordinate system, that's 1, -1. Okay, but we now have the S to B matrix. (6/5 minus 1/5 is 5/5, which is 1. -3/5 minus 2/5 is -5/5, which is -1. So instead of having to draw the picture every time, all we need to do is use the matrix to do the conversion for us. So let's just try another one. So S will always be the standard coordinate system, the X and Y axis that you learned about in first grade. And the B is going to change for us. So in this problem, B is now that coordinate system. So the picture should be there's your X, there's your Y. There's X hat and Y hat. It's two typical problems here is I give you the B coordinates and ask you for the standard coordinates, or give you the standard coordinates and ask you for the B coordinates. Let's try this first one. Oh, so before we get started, the B to S matrix is easy to make. It's just take the vectors that make up B and drop them into the columns.
Is there a, maybe on the origin, you just do that with an example?
Oh, this is just another example. So I took the standard coordinate system, made up another one, and then this is what I want to do. So the S to B is the inverse of this, which is 1/2. So the first problem, we're given B coordinates. We want to find the S coordinates. So we've got we apply the B to S conversion matrix to the B coordinates. The coordinates of V relative to S. So that second problem, is we use the S to V conversion matrix. Okay, so you don't have to draw pictures for these. So we can just do it this way. I'm just realizing I probably made a mistake in these earlier examples before I forgot to change it. Okay, so we've done this problem twice already. So a horse has one head and four legs. A human has one head and two legs. So I'll remind you in a bit about the two different ways we used to solve this problem. I'm going to show you an alternate solution. So I'm going to give the clever solution, and then I'm going to translate this into the language of linear algebra. So a hypercentaur is a human plus a horse. What's that? Oh, so how many heads does a hypercentaur have? Two. And how many legs? Right. But a regular centaur has how many heads? And four legs, right? So our hypercentaur has two heads and six legs. So an anti-centaur is going to be a human minus a horse. So how many heads does an anti-centaur have? Right. And how many legs? Nope. -2, right, good. So human has 2 legs, the horse has 4 legs. If you do a human minus a horse, 2 minus 4 is -2. So an anti-centaur has 0 heads and -2 legs. Okay. Oops, hold on. Yeah, I guess we can do it this way. Okay. When I see 75 heads, how many hypercentaurs are there? So, yeah, 37.5 hypercentaurs. Okay, so because an anti-centaur doesn't have any heads, then it's the head count tells us exactly how many hypercentaurs there are. And 37.5 hypercentaurs have how many legs? Gotta work this out.
6 legs.
How many? 6 legs per hypercentaur. So 6 times 7 is 42, 45. Oh, wait a sec. Did I do this right? Oh, 225, right? Yeah. So if I just had hypercentaurs, I would have 225 legs. But if I put some anti-centaurs in there, that's going to reduce the leg count. I want 200 legs. So how many legs do I have to lose?
You have to lose 25.
So how many hypercentaurs? Yeah, so I lose 12.5.
That was anti-centaurs.
Oh, anti, right. Oh, no, so it's plus 12.5 anti-centaur. So every anti-centaur gives us -2 legs. So we have 37.5 hypercentaurs and 12.5 anti-centaurs. So it's 37.5 human plus horses and 12.5 human minus horses. So this 37.5 humans plus 37.5 horses, 12.5 humans minus 12.5 horses gives us the 50 humans and 25 horses. So we've solved this problem twice before, and here is a third solution. So let me explain what's going on here. So let's go back to our chapter 1 solution, or chapter 2. So in chapter 1, in what you did in your algebra courses, was translate that to a system of equations, elementary row operations to solve the system. What we saw in chapter 2 was we imagined we had a transformation where the input was a vector representing the number of horses and heads, and the output are horses and humans. And the output was a vector in the legs versus heads space. And then we had 75 heads, 200 legs. That's our target output vector. We've got a matrix that transforms a horse head vector. So if I have X horses, Y humans, the head count is 1, 1, and the leg count is 4, 2. So solving the problem is finding the unknown input vector that produces the target 75, 200 output vector. So just a quick review. So what we're trying to do was find the input here that produced that output. And we remembered that we can put this on the other side of the equation as the inverse, do some calculations, and get, is it 15,100? Yeah, 1525. Okay, so now let's talk about our new way of doing this, our chapter 3. So I'm going to keep the same picture. We're transforming from going from the horse and human input space to the head and leg output space. But this time, I'll actually be a little bit more careful. We can decorate this. But now that hypercentaur, which remember was, let me write it slightly differently. One horse plus one human. So here's the hypercentaur vector. And since we could have more of them, we have is a new coordinate system where this new x-axis is the number of hypercentaurs. And remember, an anti-centaur, so as a vector, that's the 1, 1 axis, one horse plus one human. And the anti-centaur, which was 1 horse plus -1 human. I guess we're doing these in the same color. Here's y hat, which is the number of anti-centaurs. Okay, so then, I'll do it this way. Do that blue, that works. We're going to look at that same map from, this time from the new coordinate system. So, see if I have, let me do this. So the number of heads is just going to be 2. So it's 2 heads per hypercentaur and 0 heads for each anti-centaur. And then it's 6 and -2. Okay, so there's the matrix that transforms a hypercentaur anti-centaur input to the head-leg coordinate space. And once again, we had 75, 200. That was our target. Now what happens is whenever we move in this direction along the hyperaxis, that's going to give us a vector here. So we know if we travel 37.5 units along this new x-axis, oops. So 37.5 units along there brings us to 75, 225. And then this is the key. It's when I move in the positive y direction here, that goes straight down, is I don't move in the x direction at all. When I went 12.5 units in the input space in that direction, that was 25 units down in the y space. So the solution to this equation, and I can do this without finding the inverse, is x hat y hat is 37.5 and then 12.5. So our B basis was the hypercentaur and anti-centaur. The standard basis is horses and humans. And then we got the coordinates of our solution relative to B. And what we want to do, the original question was to find the coordinates of V relative to S. And then we've got to convert, we've got a matrix that'll do it, the B to S matrix. take this, apply it to this input, and that gives us the 50. So the punchline here is that it was easy to know how many hypercentars we needed because of this 0 in the matrix. So the head count completely determines the hypercentar count. So we know because the x coordinate over here was 75, without computing an inverse, we knew how far along to go in that direction. And then we did the correction. We needed to drop straight down. We already had the head count dialed in. So we knew when we moved in the y direction, that's just moving down here. So given, this is going to be a theme that we're going to hit in chapter 7 and chapter 8, is given a matrix that represents a transformation, we want to come up with a different coordinate system so that the transformation matrix relative to that coordinate system has a lot of zeros. So the more zeros we have in the matrix, the easier it is to make the calculation. So let's talk about this. Summation. Yes.
Here's some info about summation.
Inputs and outputs are given. Relative to B. Okay, so here's the idea. We imagine that we're mapping S inputs to S outputs. And there's the matrix that does it. Okay, now I've got this coordinate system. Actually, decorate this up here. I want to take B inputs to B outputs. And what's the matrix that does it? So let me do a specific example. So let's say I've got I think that'll work. Here's the 4-2 input vector, 12, that goes to 14. 8. 1410, I think. Is that right? 12, 14, 4, 6, 10. Yeah. Okay, but 4, 2, relative to this coordinate system, so that same vector is going to be 3 of those, and this is going to be down here. It's the 3, -1 is the input. And then 1410 is going to be 12, -2 as an output. Okay, so same vector, just written relative to the different coordinate systems. So we've got a matrix that does the transformation when we're writing relative to S coordinates. I want to know what matrix do we use here that's going to turn the input written relative to the B into the output written relative to the B. So that's what we're trying to figure out. If I want to turn B inputs to B outputs, what matrix do I use? Okay, so yeah, let me draw the picture here. B looks like this. So I want to start with a B input and end with a B output. Instead of going directly there, I'm going to make this a 3-step process. So I'm going to go from B input to standard input. Then I'll go across from standard input to standard output. And then standard output to B output. So what I want to do is B input to B output. Go 1, B input to S input. Step 2, let's go from S input to S output. Then convert that S output to a B output. Okay. Remember, we've got a matrix that takes B coordinates to S coordinates. So remember, our B basis is this. There's the matrix that does it. What's the matrix that takes S input to S output? Well, that was given to us already. And then the matrix that takes S coordinates to B coordinates is the S to B matrix. which is the inverse of the beta S. Write that a little bit nicer. Okay, so we've broken it down to a 3-step process. Let's write it this way. So yes.
So when you're translating it to an S to B matrix and you're doing the inverse, is it always going to be 1/2?
No. So remember in general, the formula for a 2x2 inverse.
Oh, right.
So I just use that formula.
Okay.
So step 1, is beta S. Step 2 is B. No. Let's write it this way. And then step 3 is S to B. So then we talked about how to combine matrices. I'll assume you can do this. You were tested on it. I know. See if I can do it. So that's 4. Oh yeah, it's -2. That's right. That's 4. That's 2. That's 4, 0, 0. Okay, so there is the matrix that will turn B inputs to B outputs. So clear. We actually know what this is. I'm really giving you a preview for chapter 7 here. The idea is, given a matrix, we want to find a coordinate system. So the new matrix relative to that new coordinate system has as many zeros as possible. So when I had this matrix, I knew that this basis would produce a diagonal matrix here. Doing on time. Oh, we're over. Okay, so we'll keep talking about this on Monday. Thank you, students. Can I talk to you gentlemen for a minute? So, oops, excuse me. Hey, hold it. Oh, this is more my job as a teacher. So I look back there, I don't think you two heard one word that I said. So I'm not quite sure why you're coming to class. So So, I mean, like I said, your education, you do what you want. but
Yeah.
I think you're not getting as much as you could out of class. Yeah. Take care. Take care.